Hello again, so this is another video by Structural Analysis, made fun and easy. This is for a cantilever beam. Again, this is just a really simple video. 7th of September, I'll cantilever with a point load right at the end. This is Structural Analysis, made fun and easy. It's the 7th of September by me, Richard Julian Nash. Please like the channel and subscribe to the channel. Yeah, please donate if possible. I'm going to put a link so you can donate, so I can keep doing these videos. This is really intended for B.Eng Honours, M.Eng, MSc, even people who are moving up as well, be even more useful. HNC, HND, Civil Engineering Theory of Structures. So today in this one we want to determine the deflection of a cantilever under a point load at the end. So here we got our orange, that's the point load P. Here's the beam again. This is fixed at the end. The length of the beam is L. So we start from the right hand. When we're doing the analysis, we're going to measure X from the right hand moving left to X. P is the point load in orange. So just another little note about multiplication. Unfortunately, in our alphabet, the letter X is also used as X multiplication, as it can cause confusion. So I'm using between numbers or terms. So I'm using dot between numbers or terms to mean multiplication. So basically, in this equation, it doesn't get any more simple than this. The moment at X is equal to P times X. So basically, you've got a moment diagram. It's going to look like this. As you move from, that's because X moving along as well. At any point along the beam, moment's going to be px. So it's the same when we're at the support. When X equals L, the moment's going to be P times L. So equation 1 is M equals Px. Equation 2 is M equals EI d2y over dx2, which is the second differentiation of y. Y is, remember, y is the deflection, dy over dx is the slope, and d2y over dx2 is the moment. Just if you can just remember that, I'll just say it one more time so it goes in. Y, where you've got a beam with length x on the horizontal axis, y on the vertical axis is deflection, dy over dx is the slope of the deflection, d2y over dx2 with the EI is the moment. So then you've got simply equation 3. So what I do, make equation 3, just put equation 2 equal to equation 1. Moment equals d2y over dx2 equals px over EI. That's equation 3. So the second differentiation is px, basically. That's moving from the right to the left. So basically, what I'm going to do now in this video, remember we got px over EI. So instead of me typing out EI 100 times or whatever, I'm going to just take that out. We put EI back at the end. So whatever equation whatever we get on the right hand side of the equation on the x, we're going to just put the EI back at the end. So we need to do the first integration of px to get the slope. So integrate d2y over dx squared over px, equation 3. That gives you dy over dx equals px 1 plus 1, so that's px squared, and divided by 1 plus 1 plus c1. So c1 is called the integration constant. Dy over dx equals px squared over 2 plus c1. What is the value of c1? We use our boundary condition, so this equation is the slope. We know that at the support the slope is 0 because the end condition is fixed. Therefore, when x equals L, slope equals 0, dy over dx equals PL squared over 2 plus C1. So you just put L equals X in equation 4. put L equals X, PL squared over 2 plus C1. So we know when X equals L, that's at the support, slope equals 0. So dy over dx equals 0. Therefore substitute that back into that equation. Substitute that back into the equation, get 0 equals PL squared over 2 plus C1. Rearrange to find C1. C1 is equal to minus PL squared divided by 2. That makes sense really, doesn't it? Because you've got dy over dx is PL squared over 2 plus C1. dy over dx equals 0. 0 equals PL squared over 2 plus C1. Take PL to the other side. C1 equals minus PL squared over 2. So that gives us the equation dy over dx equals px squared divided by 2 minus PL cubed divided by 2. So we have a consistent equation, so that's the equation for the slope. Now we need to integrate again, the second integration, to find the deflection. So we're going to integrate equation 6, integration of px squared divided by 2 minus PL squared divided by 2. Y equals px squared, px 2 plus 1 divided by 2 divided by 2 plus 1 minus PL squared x 0 plus 1 divided by 2 divided by 0 plus 1 plus C2. So y equals px cubed divided by 2 times 3 plus PL cubed x 0 plus 1 divided by 2 times 1 plus C2. So equation 7, that's a deflection. The deflection equals to px cubed divided by 6 minus PL squared x divided by 2 plus C2. So that is the equation. We found that out. As I said before, so this should have EI on it. I've done it. Should be in capitals as well, but I said I'll put that back at the end. But we've just got one more thing to do. What is the value of C2? We use our boundary conditions. So this equation is a deflection. We know that at the support the deflection is 0 because the end condition is fixed. Therefore, when x equals L, deflection equals 0, y equals 0. So y, in equation 7, y equals 0 on the left, x equals L, so it's 0 equals PL cubed divided by 6. It would be EI, but I'm putting that in at the end, minus equation 7 again, PL squared, x is equal to L again, so it's PL squared times L divided by 2 times 1, so that's just 2 plus C2. So if we rearrange it, then we get C2 equals PL cubed, PL cubed divided by 6 I've made a little mistake with the signs there. That should be minus, and this should be plus. So C2 equals minus PL cubed over 6 plus PL cubed over 2 is equal to 2, so it's 1 over 6 minus 1 over 6 plus half, so that's plus 3 over 6. Minus 1 over 6 plus 3 over 6 is 2 over 6. 2 over 6 is equal to 1 over 3. C2 equals PL cubed over 3. So PX cubed divided by 6 minus PL cubed. So we put that back, so now we've got C2, we put that back into equation 7. PY equals PX cubed divided by 6 minus PL squared x divided by 2 plus, that should be, plus PL cubed divided by 3. So all they should have EI on them underneath, but now we can put that EI back underneath it. That gives us equation 8. Now we have a consistent comprehensive solution for the y deflection. So y equals px cubed divided by 6ei minus pl squared x divided by 2ei plus pl cubed divided by 3ei. So what we want to do, just to finish this off, we want to know where y when x equals 0. Put x equals 0 into equation 8. Y equals px 0 to the power 3 because x is now 0. So that term is 0. put PL squared y equals P0 cubed, so that's 0, minus PL squared 0, so that's 0, and that should be plus PL cubed divided by 3, and that's EI. So y equals 0 minus 0 plus PL cubed divided by 3. So y equals PL cubed over 3 EI. Okay, yeah, I just need to check the signs, what I've done with the signs, but basically that is the equation, that's the solution to this. So you get PL cubed divided by 3 EI. Let's just check that again quickly. Yeah, m equals d2y over dx2 plus px over ei, d2y px, dy over, so the slope is dy over dx px q squared divided by 2 plus c1. Yeah, c1 is minus pl squared over 2, dy over dx equals px cubed, px squared divided by 2 minus pl squared over 2, px squared divided by 2 minus pl squared divided by 2. Integrate this equation and you get, oh yeah, px to the power of 3 divided by 6, pl squared x1, x to the power of 1 divided by 2ei plus c2. So c2 must equal to, oh, it's plus a half. Yeah, it's got to be plus a half minus a sixth. Plus a half minus a sixth. Yeah, that's it, isn't it? Plus a half minus a sixth, plus a half minus a sixth, plus a half minus a sixth, plus a half. Sorry, yeah. Plus a half. Oh. C2 equals, hold on, yeah. C2 equals, if you take these two to the other side, it's going to be, that's plus, sorry, yeah. That's where I've done it wrong. So 0 equals PL cubed divided by minus PL cubed divided by 6. Oh, 0 equals where did I get to? It was px squared over 2 minus pl cubed over 2, px cubed over l, pl cubed over 6 minus pl cubed over 2 plus c1. It should be plus a half minus 1/6. That's equal to 2/6, 1 over 3. That's c2 equals to plus pl cubed over 3. So p is, oh yeah, that's it, plus, yeah, plus pl cubed over 3 ei. That's the answer. The deflection of a point load at the end of a cantilever is pl cubed over 3 ei. This was another video. Please like and subscribe to the channel for more of these videos. Thanks.